No, it's easier. Well, now I'm live. Okay, so slide this which way? Here we are again, session 3. That looks good. Good enough. Try to have some stuff off the margins there. So this one we're going to do VSEPR theory, intermolecular forces, which is going to be covalent bonding, which is part of VSEPR theory. And then we have ionic bonding and metallic bonding. That is going to be really short, and then maybe a quick snippet about covalent network. But honestly, I'm going to focus on VSEPR theory, intermolecular forces, which are hydrogen bonding, dipole-dipole, London dispersion, and then there's a possibility of polarizable London dispersion forces. They're all called van der Waals forces, though. So there's some books and students and teachers that disagree, but they are called van der Waals forces, all of them. Okay, so here we go. So we're going to start with something really simple. We're just going to pick a molecule. If this is a AP Chem group, you should have been dot structure knowledgeable. So let's just start with the most common molecules that we know on the face of this planet. So let's just start with a molecule that we know is covalently bonded. It has all nonmetals, okay? And it's not network. Network are going to be your graphite, diamond, quartz, stuff like that, okay? So this is an individual molecule that would be a H2O by itself, and then maybe another H2O over here, depending on the state of matter. So step 1, okay, this is easy dot structure. Step 1 is to count, the easiest thing to do is count all the valence that you have in that molecule. So for hydrogen, it has 1 electron, but there's 2 of them. So I just kind of do a little arrow here. And then oxygen, this black marker is done. Oxygen has a valence of 6, right? Yes, okay. And so this total structure will have a total of 8 electrons in its dot structure, okay? So if you don't have the dot structure rules, you can get them. My students, I'm going to grab something really quick here. Here we go. Feel Emma's here. There are a bunch of students behind me here. I'm going to say hi to them. They're hopefully going to ask questions or answer things, but we'll see. So they have this, okay? And they did their dot structure notes here. So they have all the rules. So right now they're really just reviewing for the AP exam, trying to make sure they can still do all this with some harder ones, because the AP test is going to ask you harder ones. So they have the rules. So you might want to get that. The other thing you might want to have is a periodic table so that you can find the valence, along the top of the table. Okay, I'm going to hand this back to Emma. Yes. Here we go. So next thing to do, I would do is count how many pairs. So there's going to be 4 pairs, because you're going to place these electrons in pairs. Next step is to say, of these atoms in this dot structure, which atom is going to take the center position, and that in this case, it's oxygen. It's either the least electronegative, which is the best thing, or it's the atom that is written first or the only one. Now for oxygen, hydrogen is always peripheral. So this has a higher electronegativity, but yet it's still in the middle. Then you just go top, bottom, left, right, like a north, south, east, west, okay? And put your center atom in the middle. This is a dot structure. This is not 3-dimensional yet. Then the first rule is to put a pair between these to bond. So you can put a pair like dots. If you don't want to draw the line right away, you don't have to, but that's going to signify that this is a single bond because it's between 2 atoms, between the hydrogen and the oxygen, etc. Hydrogen follows something called the Duet Rule, which means it only prefers to have 2 electrons in its pair. There's the Octet rule, which says that typical atoms will have 8 electrons, and then there are what are called expanded octets. And expanded octets just have more than 8. So those are your choices. So for this scenario, hydrogen has 2 electrons bonded. It's following the Duet rule. The other pairs, you'll put them as what are called lone pairs. Okay. Now, after you do the lone pairs, this is not done. So in first year chem, that might have been all you did, so that you can say that there's 2 single bonds. These would also be 2 sigma bonds, because there's sigma bonds means that this is the name of it, sigma bonds. Let's just cover this right away. Sigma bonds means it's a bond between the atoms. Pi bonds are bonds with p orbitals. So that was the video that I just had out there about shapes and orbital shapes. P orbitals that are not used for sigma bonds can be used for pi bonding, and they're like above or back and forth in a molecule. So to have a pi bond, you would need to have a double bond. A double bond has one pi bond and one sigma bond. And then a triple bond, which we haven't had yet, has two pi bonds and one sigma bond. So you always have a sigma bond. A single bond, like this right here, is just one sigma bond. A single bond, I said that right. A single bond is one sigma bond. That's it. So that's the short way. So if you're ever asked that, that's the fastest thing you can do. Is just say single is a sigma, doubles a pi and a sigma, and a triple is two pi's and a sigma. Now, if you do hybridization, you can really go over better why. But for AP Chem, it might come up, and that'll get you far. That's all you need. So we're not done yet. We have to do the VSEPR shape of it. So what I have my students do is say, you have an atom in the middle, count how many regions are around. It's 1, 2, 3, 4. So this is a 4-domain or 4-electron region molecule. So what they'll do then is they go to their foldable and they'll say, these are the options. So if I was a region, the first choice, I'm just going to do it like a stick figure here, is what's called a tetrahedral shape. So you have an atom in the middle, bonded to atoms here, here, and here, and here. And then these are three-dimensionally trying to show it goes back. So it's tetrahedral. That is not what we have, because that would be where all our four regions are bonded. So then another choice for this is trigonal pyramidal. Okay, so it's a second choice for a 4 region. So trigonal, and then pyramidal. That's if you have 3 that are bonded and 1 that's a lone pair. I'm gonna have to get a new black marker. This one's bad. I'll try this one again. So there would be a lone pair, which takes up more space. So keep in mind, on the AP test, they'll say that the bond angle here is about 109.5. Your choice is either to get the right bond angle or say that this is less than 109.5. Common is 107. So that's important in AP Chem, that you know that this lone pair takes up more room and it shoves those bonded regions down and makes this bond angle right here less than 109. Last choice is you have a center atom to these outside atoms, and then there's 2 sets of lone pairs. And this is called bent or V. You're going to see people use both, okay? And then this is sort of less than 109. The other thing you could do is 104.5 is very common, okay? So 104.5. So they're saying this angle between here is 104.5. So you have 3 that are bonded and 2 that are lone pair. Now, if you have a teacher, or I have shown you this too, some teachers will call this an AX4. A is the atom in the middle. X are any of the ones that are bonded, and it means 4 are bonded. Okay, some professors are super into this. Okay, I'm just telling you, I'm not, but they might be. And then AX3E1. So I have a student teacher, Mr. Carlson. I've said him in every video, but hi, Mr. Carlson, back. But he just finished his chem degree, so I don't know if his professor was into the AXE. They usually are. He's shaking his head, absolutely. Just don't be scared. They're just saying bonded and not bonded lone pair, okay? So this is called an AX2E2. Even when I say it, AX2E2. Okay, Josh, how are we doing? Okay. I'm picking on Josh. This has been 3 times. He's like, please stop. But he's learning some of the stuff for the first time. So we got to make sure Josh is okay. Richmond. Yes, thank you. They're catching it. We're live, so I'm almost happy I have a group of students back here. I have a Richmond and an Eli, like, you wrote something wrong, so thank goodness. Okay, are we good now? This is hour number 3. It is freshman testing. These are juniors, sophomores, juniors and seniors who decided to get up early, come to school, sit and listen to me blab about chemistry so they can hopefully pass the exam, maybe even get a 5, right, Dane? Yes, let's put it out in the world. Okay, AX2E2, are we good? So Josh, moral of the story here is we have water, one of the most common molecules that we ever want to know. 4 regions. It might be called, be careful, these are called, I think they're called the molecular geometries. This is picky. This is uber picky in my opinion. these are the possible molecular geometries, okay? But they all have a electron geometry. To me, this is nitpicky, but I've seen it out there. They all come from a electron geometry of tetrahedral. So be careful if they say, what's the electron geometry? The answer for water is tetrahedral or 4-region. But the actual molecular geometry, to me, this is picky. I wouldn't do this to students, but some people do. The molecular geometry is bent, okay? So they're just saying that it comes from a 4-region. You have 2 lone pairs, though, so then you have 4 regions, which should have a tetrahedral kind of shape. But because these 2 regions are lone pairs, you lose that, and you end up just having a bend, okay? The other thing that's important, and we won't say why, sorry, Eli, I'm going to say that for the rest of the school year. We can go over it after the test. These are all going to be sp3 hybridized. What does that mean? They're going to take an s orbital. I'm not explaining why. That's a whole other video. And they're going to take 3 p orbitals. They're going to hybridize them, and they end up looking like this. So this is a hybridized sp orbital. And then when you connect these together like this, I won't say why they look like this. Oh, I'm not very good at drawing it. They will make this tetrahedral shape. So an s orbital, I had a video we just did today. That's how this all relates. That's an s orbital. A p orbital looks like that. Okay. It's on the screen. Try to make sure it's on the actual screen here. An sp3 orbital looks like this. I'm going really over the top. So it's got really big lobe and then a little one, okay? And if we didn't hybridize, we wouldn't have tetrahedral. That's the short version, okay? So if on the AP exam, they ask you the hybridization of water. It's very simple. It's sp3. It's the answer, okay? If you add these up, this equals the region. So this is a 4-electron geometry region. Okay, in the end then, what we would do is we would draw water like this. So this would be how we would draw water with kind of chemical bonds. And this is our oxygen. These are our hydrogens. Make sure it's on the screen. Yep. Okay. But don't be shocked if you'll see people just draw water, you know, kind of like that, where it looks a little like a Mickey Mouse. These are the same thing. This is just called the space filling model. And you're going to see that a lot when we get to intra and intermolecular forces, the difference. So right now, let me just kind of say the difference a little bit with a color. This bond right here and this bond right here are an intramolecular force. It's the force inside the molecule, okay? So when we do this dot structure, I'm going to do a couple things here. Next, I'm going to have us look at electronegativities, because intramolecular forces, you would say that this is a covalent bond. We're going to add polar and nonpolar in a second. So it's a covalent bond. It's not ionic because it's between 2 nonmetals that are sharing electrons. They have difference in electronegativity we'll deal with in a second. But it's an intra, okay? This is just one of the types of intramolecular forces, this covalent bond. And what I want us to do is throw in polarity right away. So the next thing, if we go back to the first video I made today, was about periodic trends. So if anybody's watching, all 3 are my students that are sitting here, bless you, for sitting here for 3 hours, this is all coming back, because electronegativity is one of those periodic patterns that comes back to where is it on the table. The electronegativity is the ability to pull on electrons in a bond. I need its number. Now, you don't have to know it on the AP test unless they give you a list, but what is it? So what my students have in their full bowl an electronegativity table already glued in. So what's the electronegativity for oxygen? Nice and loud, somebody. Anybody? Hang on, crickets. Wait, where's my coffee?
Where is your coffee? Oh,
there it is. Oh, wait. So
3.44.
3.44?
Mm-hmm.
And is hydrogen 2.1?
2.2.
2.2? That makes it, I like that. That's better. Okay, so the first thing we're going to do to decide if the bond is polar, non-polar, or ionic. Okay, that's kind of how you basically say, oh, we're not covalent anymore. The difference in electronegativity is so large They're really gaining and losing electrons, which is ionic bonding, which is another type of intraforce. Got it, Josh? Here we go. So you just subtract the numbers. Make this simple. Now, if you don't have a periodic table, you just kind of have to estimate. But the difference here is what, you guys? So 1.24? That right? It's well within what's called the cutoffs, okay? So let me give you the cutoffs. I'll put them right here. So for something to be polar, most people say that it needs to have a difference of about 0.4 or above. Now, here's where you would have to find your teacher's preference, but for the AP exam, I can kind of say that 0.4 is probably okay? So we'll be all right with that. Non-polar, there are some people that say that non-polar has to be just 0. And I can't argue with you, I kind of agree at times. However, most people say between 0 to 0.3. The difference in electronegativity is so small that really we're kind of say that those two atoms are sharing fairly equally with the electronegativity. And then the difference for ionic, I'm going to put it above, usually 2.1 or greater. But honestly, you're going to have a few times where the difference in electronegativity is not 2.1, but there's a metal and a non-metal, so then you'd probably say ionic. There's also a tiny chance that the electronegativity is very large, but they're two nonmetals, and you would just say that it's really polar. So just be careful with what atoms you have. So what we're going to do, though, is we're going to say that this bond is polar. So we're going to call it a polar covalent bond. It's an intramolecular force. And the next thing we're going to do is add an arrow to it. So what you'll do is say, well, where are the electrons going? They're going closer to the oxygen. Now, a dot structure when we do molecular polarity is not a good idea. Write this down or listen. I'm going to get really close. And I'm going to try to get as close to them as I can. Do not use a dot structure to predict molecular polarity. Okay? Because right now, if I do that, I'm going to probably say that water is non-polar or non-dipole. It's wrong. Okay? So you got to go to a dot structure that has to turn into a VSEPR structure. So when I draw this arrow, I'm really drawing it like this, okay? So it's coming up towards the oxygen at an angle like that. Same thing here. So you would say that this has two, you could even say it has two polar bonds. The electrons are going up and getting pulled up to the top, which causes there to be a partial positive because the electrons are moving up that way. So they're not here, down here. And up here, you can talk about the lone pairs if you want, but really the electrons are heading up towards that top end, which makes this molecule then be a polar covalent bonds. However, the molecule right here is a dipole, or it has a dipole, two poles, or more commonly, we'll say that this is a polar molecule. I'm trying to write this really big. We can see it. Good. So this is the classic polar molecule. It has a dipole. I want that because when we do intermolecular forces, I want you to know that this has a dipole because we're going to call that this has a dipole force and more. Okay. But right now, let's just focus on the molecular polarity. Now, I'll be honest with you. Most of the time when you have pyramidals and bents, they're going to be polar molecules. Tetrahedrals can go either way. It just depends if your tetrahedral has the same things on the ends, like that, or if it's lacking kind of some symmetry and it has a different atom, right there. So be careful, tetrahedrals can go either way, but chances are a pyramidal and a bent for 4 regions is going to be polar or a polar molecule, okay? Because they will have what's called vectors heading in one direction. So you're looking, does it have a positive, negative bend? Now, that's a lot of time. A lot of students struggle at this, so that would be completely something you need to tackle a little bit on your own. I'm going to do a couple more molecules, and I'll add this in. So this was just 4 regions. There's 1, 2, 3, 4, 5, 6 region molecules. So this was just only 4. All right, let's keep going. We're going to go to some harder ones. So I'm going to jump into the SO4. I'm going to leave this up here because we can use this for just a little bit. So we're going to use sulfate. So to me, this is like, level 2 of this VSEPR theory game, which is 2 months, okay? So when you have the minus, you're going to still say sulfur has 6 valence electrons, oxygen has 6 valence electrons times 4, but you get to add 2 more because of that charge. So the first thing you do is add that all up. So I'm going to have my students kind of yell out what it is. So 24, right? The 32 electrons total, but to be honest with you, it's easier to think of that as 16 pairs, okay? Now, for this case, it works out nice. Sulfur is the least electronegative. It's the one first in the formula, and it's the only one in the formula. So it catches all those choices that it's in the middle. Then again, we're going to live in a land of 2 dimensions for a little bit, top, bottom, left, right. We're going to take the pairs and bond them. So there goes 4 pairs right away. And then I tell my students, before you even do any more, always on the AP exam, make sure that you have brackets in a charge. Ions, brackets, charge. If you forget those brackets in the charge, chances are you're not going to get the points. Okay? I'm pretty sure I can even say like 99.9%. So put the brackets in the charge. Now, for my students, I say usually oxygen likes or prefers, we can do formal charge in a second, to have 2 pairs of lone pairs like that. Okay, so I say just do that right away. Its chances are pretty high that that's going to work. How many pairs have I placed? Because we have 16. 4, 5, 6, 7, 8, 9, 10, 11, 12 only. Okay? So then, if you think about it, your tendency is to do this. 13, 14, 15, 16. Now, in first year chem, I would say go for it. Let that be right. You do not need to tell a first year chem student that they're wrong. Is that going to be tetrahedral shape? Yes, okay, but it's an ion, so I wouldn't worry about, is it polar or not? It's an ion, so it's negative, so be done with that, okay? However, there's something funky going on with this one and another one, okay? I need us to use formal charge, okay? So this is formal charge, the formula. And we'll do the dot structure turning into a VSEPR shape in a second. But anyways, it's still going to be 4 readings. So formal charge is a formula that says this. You'd have the number of valence electrons in an atom that you're looking at. You're going to then take that. You're going to subtract it from another quantity where you find how many electrons are in the bonds. It's the total number of electrons in the bonds. And then we'll put a bracket here. Plus 1/2 of the number of lone pair or lone electrons. Now these are not, don't count the pairs in this case with this formula. They are the actual number. Okay, let me show you something about this. It's a lot of times this is in a second year book, this ion especially, and then another one I'll show you. So what you're going to do is you're going to say formal charge is, so let's do one at a time. You put an S for sulfur. Has 6 valence minus, how many are in bonds? All. Plus, I'm going to make sure I got this formula right, plus 0. So I'm just going to kind of check with my AP students behind me. Do I have the formula right? I think so, right? Look here, you got a cheat sheet and look in the book a little bit here. Make sure. On the AP exam, you do need this formula memorized.
I think the 1/2 is with the bonded.
Is it with the bonded ones? Check here. It has to be because this is not making sense. Yep, so this is wrong. Rewind here, go back. This is with the, this is the lone pair electrons. This is the bonded ones, good. Student teacher saves the day. You do need to memorize that though. Okay, if not, I knew something was wrong because I kind of know what the formal charge for this should be. So this is actually a 0, and then this is the 8. Okay. So that is 6, 0, and then this is going to equal 6 minus 4, which equals plus 2. So I kind of knew that was the charge. That's how I knew something was wrong. So what we'll do is we'll say this has a plus 2 formal charge. This is not looking good. Formal charges for molecules, we would prefer them to be 0s or 1s. That means it's more stable or likely. So it's about predicting the likelihood of a dot structure, okay? This is not looking good. So then let's check the formal charge of the oxygens. Benefit to us is they're all the same, okay? So then you're going to say 6 minus, and then this is the lone pair, which is 6, plus 1/2 of only 2. So then you get this equals 6 minus 7 equals -1. So then this has got a -1 formal charge. This is -1. This is -1. This is -1. Now, here's the beautiful thing about formal charge if you mess it up or you're not sure you got it right. The formal charges for each one have to add up to equal the charge on the molecule, whether it's 0 or in this case 2 minus. So does that, when I put that together, equal 2 minus? Yes, we know we did it right. That's the way to check it. In case you get on AP test, there's a lot to remember. So there's, this formula, they don't give you this. Let me say that one more time. They don't give you this. So if you do like I did and kind of mess it up, we'll say me back and did that on purpose. I did it though. It's human error. You need to kind of put that to memory or something else. Okay, so -2 works out. Now the problem is what happens is this. Let me just show you this. You could have a possible resonance structure, and I'm just going to cut to the chase, because sulfur can expand its octet. So the atoms that can expand their octets have to have atomic number 15 or greater. So I'll say that atomic number 15 or greater, they can expand their octet. That's our school day. We're going to go fast now. The expanded octet is possible. So let's prove why that possible dot structure wins, even though in first year chem we wouldn't expect the student to do that. So what'll happen is, let's check this again. I'm going to leave these two the same. Are you okay with that? That they didn't really change? So let's check the double bonded oxygens now. So this is the single bonded oxygen. This is the double bonded oxygen. So 6 minus, how many are in bonds? 4, plus 1/2 of, in this case, 4, right? So then this is 6 minus 6, which is 0. So now these are lower. And then we got to go back and fix this one. It actually has still no lone electrons, but it has okay with the fact that it did 12. Okay. It has to have d orbitals to expand its octet. So if again, I want to go all the way back to where we started with other videos. To expand your octet 15 and greater is because they have d orbitals within horizon, is what I call it. This turns into being 0. Do we still get a total of -2 in the molecule? Yeah, in this ion, that's a molecule. Okay? It's an ion, but still to me a molecule. It's a covalent molecule. That's an ion. And that has lower formal charges, so then it wins. So that's common on the EP test where they'll say, they may not say do it, but they may say, why is this the more predicted likely structure of the resonance structures that are possible? Okay. Resonance just means we keep all the atoms in the same place. We just have different types of bonds, singles and doubles and triples. Okay, Josh, how are we doing?
Good.
So resonance is just a fancy word. Resonance is a fancy word for saying we can have different dot structures. All the atoms are still in the same spot, though. We're just having different types of bonds. So, Josh, what we would do is you put arrows between them, since this is new to him. And I won't do all of them. Put the brackets first. Do not lose your points on that. And then you would do the original one that you probably would put in a first-year chem class. And you'd say, yeah, this is the answer. In fact, I would expect students would tell me this is the answer. And I'd never tell a first-year chem student that they're wrong. Okay? Let them learn first and then tell them their exceptions later. You can put the double bonds any 2 places, but I'm going to put them this left and right. And now, could there be other choices? Well, you betcha, because these double bonds could be top and bottom. I mean, you could possibly argue they could be left and right, but I would say for sure they might want where the bonds from the top and the bottom oxygen is another possibility. So you just show all the possibilities lined up like that with arrows in between. All right, there's a lot. Okay, we're not done because we're going to do some hard ones. But I'm going to let you kind of take a look at that. The shape of this would be tetrahedral. But because it's an ion, you would just say that this is it's got a charge on it. So I don't, put like that on it if you had to. but it would be tetrahedral, both electron and molecular geometry, and it still would be sp3. Okay, so off this goes. We gotta get rid of this. Make sure you wrote it down. Here we go. So we're gonna try one that stumped. I have an academic team, and we competed, and this one really got everybody. So I think it's worth us doing. Because if these are the, supposedly our smartest, most interested students in science that we put together, and they compete, and they got in trouble when they were asked to do the dot structures, resonance forms, and formal charge for this one. Okay, I wish I could see how long, what is up there. All right, we're gonna have to keep going fast now. So I'm gonna kind of go over here. We did that. We did that. Oh, I should have added pi bonds in there. We'll try that again. We'll maybe talk about that. We might not be able to do the other one. All right, so here we go. So the problem with this one is students didn't know where to put the hydrogen. So the nitrogen is in the middle. The oxygens are on the sides like this. But you can see, where do you think students put the hydrogen? They put it on the end. It doesn't go there. Now you might say, well, yeah, it can. No, it can't. And it doesn't, okay? So most of the time, people just pick, it's gonna go there, okay? You think about it in AP Chem terms, if we were to do acids and bases, that hydrogen is gonna be what? Deprotonated. It's gonna come off. It is gonna leave a nitrate behind and a hydrogen ion. So you kind of have to know it's sort of on the outside. This was a tough one, okay? How many total pairs? Who can just shout out how many we have? I don't want to add it all up. This is nitrogen only has 5, so 6. 12 pairs, right? Okay. So we're going to go 1, 2, 3, 4 right away. Okay. Then we want to do what we can. We have 12 pairs, so chances are oxygens will have 2 pairs of lone pairs like that. But that leaves me with 1, 2, 3, 4, 5, 6. Let's just do 7, 8, 9, 10. So that holds true. I tell my students, put 2 pairs of lone pairs on oxygen. Should be good, okay? But what's the problem at this point? We're running out. What we got? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What are we going to do? Is there really 12 pairs? Yeah, no, I was right. No, there are 12. So at this point, hydrogen, do this. Is it supposedly satisfied?
Yeah.
Duet rule done. Oxygen here? Done. Nitrogen? No. Can't expand its octet either. Do not expand nitrogen's octet. That's actually why the other one will be wrong. So if you try to put a hydrogen right here, I can prove to you, but we don't have time for that'll be wrong. You're going to want to put a double bond that will be satisfying the nitrogen and the oxygen with one more pair. That's number 11. You can put the 12th pair then over here. No expanded octets here. No expanded octets, okay? What I saw was a lot of expanded octets with the answer, which is wrong. None of these have atomic number 15 or greater. What does that mean, though, for a resonance structure? Where could we have another answer? And again, this is 3-dimensional right now. I'm not doing a VSEPR structure yet. So I have the same connectivity. Okay, that's what it's called, connectivity. Okay, put those there. Do this right away because chances are that's going to be the way it is anyway. So what would be the other valid resonance structure? Yeah, double bond over here instead. Okay. Now we do a couple more things. Let's do this first. How many total sigma bonds? 1, 2, 3, 4. Okay, so they both have 4 sigma bonds. How many total pi bonds in the whole thing? Just 1. Are we okay with that? That is super easy. Now you don't have to know why, but are you okay with that, Troy? Just being like that's what it is?
No, actually, I don't understand what a pi bond is.
Yeah, and so on the AP test, if it shows up, we might not know what a pi bond is or what a sigma bond is, but we could always add that in as a review later. But right now, we could at least get that answer correct. Could circle the right bubble. So moving on. What else do we have going on? Let's do formal charge quick. So do formal charge for each one. So the good news is whatever it is here and here, it's the same answer both times, okay? The only difference is in here it's the same both times. Here versus here is where it's different and they're just gonna swap. Here's the deal though, all the numbers that we're gonna put as formal charges have to add up to what this time? 0, okay? There's no brackets, there's no charge. Okay, so I'm just gonna tell you if you check formal charge, hydrogen here is gonna be 0. Just trust me because we're trying to shortcut it. This is 0. Let's just check the nitrogen and just see. So these are gonna be 0. This nitrogen has formal charge of N equals 5 minus 0 plus 1/2 of 8. Are we okay with that? Which is 5 minus 4, which equals +1. Are we fine with that? Everybody check it ahead of time? I'm going off the fly here. I think this is +1. Pretty sure anyway. If you check this oxygen right here, formal charge of the oxygen, it has the double bond. Okay, so double bond to the end. It's going to be 6 minus 1/2. Oh no, so not 1/2 yet. 4 plus 1/2 of 4, which that one is going to be 6 minus 6, which is 0. So this one's 0. That means it's 0 here. And this is +1. So right now you can kind of already say, what do you think the other one's going to be? Oh, I forgot some dots here. There we go. So what is that one or that one going to be? What's your prediction without even doing it? -1, right? Now how can we prove it? Let's just check. So if I'm the formal charge of the oxygen that's got the single bonds, I've got 6 minus 6 plus 1/2 of 2, which equals -1. Whole thing adds up to 0. So all it's saying is that in this molecule, this oxygen is sort of carrying a slightly negative charge. And in this resin structure, this one's sort of carrying a negative charge. But really, here's a couple things that I think we're going to have to call it today with this one. I want to do a few more things. Nitrogen in the middle is going to have a trigonal planar shape to the oxygens. Are we okay with that? So these are my oxygens. Because it's a 3 regions. 1, 2, 3. My students have a full one that they go right to that one and say they're all bonded. It's going to be a trigonal planar. Then one of these oxygens, let's just say it's this one, has a hydrogen, but what kind of region is this? 1, 2, 3, 4. So this oxygen right here has a hydrogen coming at a bent angle to the little hydrogen right there. So it's trigonal planar and bent, all in one molecule, okay? What else should we do? What else? We got formal charge, we did resonance, we've got the shapes. If they were asking you, this can happen. One of these is actually double bonded, but it can be in either position. So, but only these two. So like the bond, I don't know if you remember this, but what's the bond length and strength? So here's a triple, here's a double, here's a single. Which one is the strongest bond, the hardest to break, the highest bond energy? This is the triple. So this has the highest bond energy, the highest energy to break. And it's made up of 1 sigma and 2 pi, which we don't really know much about yet. And then the double has kind of medium, and then this one's the lowest bond energy, meaning that's the easiest to break apart. And it's only 1 sigma bond. So the bond length is the next one. Which one is the shortest bond length? Triple. So this is the shortest bond, and this is the longest bond down here. Now, what I'm getting at is this bond actually length here is always a single. So it's always going to be a single bond length amount. Whereas this is a double, or that it moves. So between these 2 bonds here, you have shorter bonds. And they're about 1.5. That's what people will call them, like a 1.5 bond, Josh. Kind of, okay? This one stays a single all the time. This one stays a single all the time. But because that can resonate between them, you'd almost say like it's got a bond length in between a single and a double. And they can measure that by breaking that bond and finding that out. Okay, so we did not get to, this is bad, because this is already 39 minutes. We did not get to intramolecular forces, so I will have to add that into tomorrow's review. And then we did a little tiny bit of intermolecular forces tomorrow. So we'll pick up that tomorrow. And that's what we'll have to do. But we still got a lot in, okay? And today was about Josh. Josh, how are you doing?
Good.
A lot of chemistry that was there, but you didn't know, and now you're good. Thank you for showing up. If anybody watched, I actually have somebody who says, hi, ma'am. Okay, so somebody to find us. And my students can watch this, and if anybody else wants to, go right ahead. It's all about getting better at chemistry.